welcome to a special video, explanation video about little bit about what happened in Southern California with the fires in the LA region, and a little bit about the wind science behind that and why those fires initiated. So I wanted to actually start out by showing you what was going on with the large scale pattern on that day. So if you could just be patient with me for a few moments as I pull up this data, I think it'll be really useful to look at to get a picture exactly of what was forcing these winds. So we're gonna go back to when the fire started, which would be January 8th. Let's go to the morning, well, when it was really bad. I mean, the 7th is when it started, but the winds were really bad on the 8th. So let's go to the 8th at, let's see, 12 Central, which will be 10 a.m. Pacific time. I'm gonna look at this pressure here. Okay, so this is what I'm talking about. So I'm gonna start annotating this here. Just wanna draw a circle. Okay, so see this area over here? Particularly over here, actually. This is a 1049 millibar high pressure center. And you look at these pressure readings, look at what the pressure is over here, over in the Great Basin Four Corners region. Over here, very high pressure values. If you go down, sorry, my computer's not collaborating with me. If you go down here, you have these pressures are generally 1038 to 1044 millibars in this whole area here in the Great Basin. And you go down to Southern California, you have maybe 1015 or so. Let's see here. Yeah, zooming in. I mean, look at this gradient. This is what I really wanted to show you here. Look at this 1041 millibars over the Elko region. And then you go down to the LA region and you're at maybe 1020-ish. This yellowish here, that's around 1020. So that's a 20 millibar difference from like Winnemucca to Los Angeles. That's very tight. That's a very tight pressure gradient. And when you have that very tight pressure gradient, the atmosphere is trying to equalize itself and the air is rushing from high pressure to low pressure. And it's doing something like this. Okay, and the wind is doing this, but this is a really intense wind because this is a really tight gradient here. So there's going to be forcing of air from high pressure to low pressure, and because of something we call the Coriolis effect, which relates to the rotation of the Earth and how that influences winds, the wind doesn't go, it's not going to go in a straight line like this. It's going to do more like something like this. It's going to do this. It's going to curve because of the rotation of the Earth. There is that. And then also terrain has influence on what happens to the wind as well. So when the wind funnels through terrain, it even accelerates. And that is something that we call the Venturi effect. Pardon, I just couldn't catch that word for a bit. It is the Venturi effect, and I'm going to show you actually. These are also known as mountain waves. I'm going to talk a little bit about that. So this happens Okay, sorry. I'm sorry. That was a little bit. That was something else I want to talk about next. But the Venturi effect, it happens when wind gets funneled through a mountain range or a pass or something like that, and it accelerates. And so as it's moving through the canyon or the pass or whatever, it accelerates even further. Now there are formulas that you can use to calculate exactly how much the acceleration will be, but to not make this video too technical, I'll just kind of give a brief explanation of what that is. And I'll also show you here, I have some wind plots for just taking a snapshot at 11:59 p.m. on January 7th, 2025 in the Pacific Palisades region, and you can see some really strong wind gusts here. This one that really stands out is in the Malibu Hills at about 2,300 feet in elevation, gusting 76 at this moment, but the maximum gust that day was 98, as we can see here, almost 100 miles an hour. And why is that? Because it's right at the mouth of a canyon, as you can see. So I'm going to demonstrate that right here with my highlighter. I want to show here what the wind does when it goes through these canyons. Remember that funneling effect I was just talking about. So it can accelerate greatly. Like, see, look at these canyons here. This is what caused these gusts here. So it's just there's so many of these canyons and the wind funnels through them. I mean, look at this 86 right here. Like there is 64. This is really strong wind. And there's something else I wanted to talk about, which is rotary winds. So for that, I'm gonna go here. So notice how most of these winds are out of the northeast. But then you have over here Topanga Beach. It's at this moment you can notice that the wind, strong wind, out of the southwest. Why is it coming from a completely different direction? Now that is due to something known as mountain waves or rotary winds. Rotor winds, pardon. So when you have very strong wind moving down a mountain, you have that wind hitting the surface at the bottom of the mountain. I'll just show you here. I'm going to highlight that. So here at the bottom of the mountain, see, it's hitting the surface and then it goes up as it's highlighted right here. For it goes in a different direction here. It moves down and then it comes and it rotates back. So that's exactly what we're seeing here. See, this is even better, like this illustration here. I can get that, yeah, here. You can see where it's coming back around here. So that's sort of what's going on here. If I now just come back here, I can show you that same effect taking place here. That's why the wind is out of the south over here, while it's coming down here and it's wrapping around. Here it's from the north, and then it just wraps, comes right back up. So that's a little bit about rotary winds. Now, let's talk about why these fires occurred specifically in these areas. Why was Pacific Palisades, for instance, more prone to this, right? It's because this area is right at the edge of all these canyons, and I was talking about the wind funneling effect. I mean, this is really dramatic to show, but unfortunately, this is what happened, and hopefully this will help explain. But I mean, just look at how many canyons are in this area, and actually, I should use my should use this instead, because they turn, and the wind is gonna follow what the canyons are doing. But look, you had a pressure gradient that was favoring winds mostly out of the north. I mean, that's like the first thing you have to consider, is that if this high pressure center, this surface high, if it were located further to the south, this would have been more of an easterly wind event. Let me show you that. It would have, imagine that this is centered over here. Would have been more of an east wind. But that's not what happened. It's centered over here. Centered right here. And if it's further north, it's going to be different. It's going to be more of a northeast wind. As opposed to, let me use a different color. Okay, so this is to compare. Say this had actually set up a little further east and south. That's the wind we would have had. And this is important to understand, because it is because this thing set up where it did, this high pressure center, the location is key. It drove the winds more of the northerly component than usual. Usually, historically, these systems tend to set up further to the south and east, more like the St. George region. And when they do that, the gradient and is more, the wind flow is more out of the east. This is a classic Santa Ana wind event. This, what we had, is not so common. Further north, so it's more of a northerly gradient. That is why we had these specific regions, such as the Pacific Palisades, being more affected. Okay, because the gradient was mostly out of the north. If the gradient were out of the east, this would not be an issue, because see, an east wind is not blasting down these canyons. It's blasting wind into different areas. Like, if it were an east wind, there are some areas, like, with, gaps facing east to west, that I would be more concerned about. Like, maybe over here, you know? Like, it would be different areas that you'd be concerned about. But because the winds were out of the north, unfortunately, it went right in to the Pacific Palisades area, and also the Altadena area does not get as much attention as the Pacific Palisades fire, but it's important to talk about as well. The Altadena fire here near Eaton Canyon, the Eaton fire, officially, I believe. And same kind of situation. You look at, like, what the winds were doing at midnight, the 7th into the 8th, for instance, as this fire was still raging. You're looking at widespread gusts into the 30s, 40s, even 50s. And if you just look at the 70 over here, it's a little further, but look at maximums. You know, no wonder you look at this 85 here, maximum gust. Henninger Flats at 2,800 feet. Same kind of concept. Remember, you know, what I was talking about, the funneling in the canyons. Look at that. Of course it was an 85-mile-per-hour gust here. Look at these canyons. Look at this funneling effect. Look at look at all these funneling. Like, of course there was a 69. Of course there was a 65. Of course there was a 99-mile-per-hour gust here. Because of the canyons and how they direct this wind and just funnel it. Accelerate it as it moves into these communities. And the Altadena area is also right at the bottom of these canyons. And these winds are just brutal. It's brutal. This is what it was, the north wind gradient. It was the north wind gradient, and it was the acceleration of winds through these areas that contributed to these fires. So that's pretty much what I wanted to talk about today. I hope this video was helpful in explaining all of this. I hope you're able to get something out of it. Thank you for watching, and I'll see you next time.